No, I think
Okay, let's begin.
Did you get no, it's not like the rate times t on the bottom of the constant. So then you
Okay, so last we discovered something called a linear first order ODE. It had the form, what was the form? Y prime plus Right, so that's the form of a first order linear ODE. You can use X or T, I don't particularly care, but that's the general form. And we saw how to solve this. We took advantage of a pattern that we saw on particular examples of the product rule. So we pretty much solved this by multiplying through. By mu, which is a function itself called e to the integral of kt. Turns the left side into, well, mu times y all prime, and allowing us to, at least in theory, easily integrate both sides and move on with our way. And I mentioned but yes, that was a very particular kind of example. It turns out that these kinds of differential equations actually show up pretty regularly in the situation where the first derivative is the highest derivative you're dealing with. But yeah, it kind of showcases the example where we solve derivatives by taking advantage of patterns that someone might see. And so a lot of times there will often not be much motivation, if any, for anything. I mean, this one, there seems to have been a slight motivation. The first guys who figured it out, it probably sort of went something like this. You know, this guy is just like trying a bunch of these first order linear problems, and he's like, I can't. I saw like 2 of these, you know, his friends, hey man, what's up? And I was like, damn it, Johnson, working out all these problems, man, and I could solve 2 of them. Then, well, what's wrong with all of those ones? Why were these easy? And it's like, well, these ones are nice because there was a function in front of the y prime and there was a function in front of the y, and it kind of looked like the product rule, and I could get that to work. And he's like, well, why don't you just try this with the other ones? And I'm like, oh, damn it, Johnson, you think something like that's going to work? And he's like, well, why can't it work? Well, how am I going to make it the product rule if it's not the product rule? And then you might say, well, you just need the coefficient of this to be the derivative coefficient of that, right? But yeah, it's not. Okay, can we make it in that way? Well, I don't know. How would I make it in that way? It's an equation. I can't just put a coefficient for whatever I want. Well, if you multiply both sides of an equation, the equation is still true, right? It has all the same solution sets. Maybe you can multiply by something that will create that situation. Damn it, Johnson, you're a genius. And then you try it, and then this pops out. Right? That could have been the story. I don't know. Like, I don't know who came up with this or why. Johnson, you're a genius. What are you going to call it? Well, I multiplied through by this factor so I could integrate, so integrate the factor. It's math, you don't get it. So we end up with the integrating factor method, which is now like the standard procedure in solving a first order linear differential equation. And it shows up often enough for you to know how to solve it, and I'm going to test you on solving these. I did test you on solving a couple of these for the quiz tonight, and that will continue. I'm pretty sure we're still in 2.2 at this point, and we're going to continue with 2.2, which talks about another class of first order differential equations. And it is the notion of what's called a homogeneous differential equation. you to know, we're going to be using the word homogeneous again, but the word homogeneous is used different in this context than every other context that we're going to use it in. So, homogeneous will be used in other different contexts later. So don't think later when we're using homogeneous things. That's when we get to higher order differential equations where we're higher than the first derivative. I'm also going to mention homogeneous. Don't think it has anything to do with this. This is kind of the odd one out. The first order differential equation is kind of odd when it comes to the homogeneous case. Anyway, let me tell you what this is. So here's the form, and at first it's not going to look very specific. dy dx equals f of xy. Right? So if you leave the derivative on one side, bring everyone else to the other side, and you notice this particular pattern where f of xy can be written as a function purely this variable, y divided by x. Now, again, that's a strange thing to notice, but it's something you could notice. Like here's an example. That's the definition. Now, I'm going to give you more useful definition pretty soon. But to motivate that definition, I want you to take notice of what pattern we're seeing here. So here's an example. Y prime equals so there is a differential equation. Now a couple things you would notice immediately, or should, is that that's not separable. Another thing you would notice is it's not linear. So the two previous techniques that we've done won't work with this guy. However, notice this kind of manipulation here. Notice that if I were to say, why would one do this? I don't know. Notice if I were to say, divide both the numerator and the denominator by x. Right? So I'm multiplying by 1 over x on both sides. What would actually happen here? This would become y over x minus 4. This would become 1 minus y over x. And now you see that y over x is the variable. And everyone else is like a constant. Like if I were to replace this with the variable, that would be the only variables present. They are all in the form of y over x. That's what I mean purely in the form of y over x. This is an example of a homogeneous differential equation. It's an equation that can be written so that anything not attached to a derivative can be written as a function of y over x. Now, these are solved using a substitution. Now, I'm going to slowly work through this one, show you how the substitution is going to work, then I'm going to give you like a summarized version of how to deal with these homogeneous equations, then we'll do a couple more examples, and then we'll move on. So, this is our new variable, so it kind of feels like a substitution of letting some other letter be that variable, the ratio, would work out nicely. And so that's what we're going to use. Typically, the letter uses v. So we set v equals y over x. Now, what are we going to do with that? Now, notice that your v is going to be a variable. Your y is considered a function of x. It's the dependent variable. Your x is the independent variable. So your v technically is also a function of x, so be aware of that. But after setting that, I can actually solve for y. I would get y equals v times x. And upon solving for that, the idea is here, I'm going to want to make a substitution. So these guys will be replaced by v's. Now the question is, what is my y prime going to be replaced by? So what I'm going to do is I'm going to find y prime at this point. How would you find y prime?
Well,
Product. Product group, right. So what is that going to look like?
V prime plus
V prime x
plus
plus v. Now, because of what's going to happen, I'm going to want you to think of this as dv dx at the moment. We're differentiating both sides with respect to x. Right? It's going to be suggestive of what we're going to want to do. So now what we're going to do is we're going to go to this equation. We're going to plug in these guys. And let's see what happens. So the y prime, I'm going to replace with that. And then the y over x's, I'm going to replace with v. What? Did someone say something? Now you can chime in. Does anyone notice anything about this equation? This new equation here with
it's separable.
it's separable. What do you mean? Coincidence? Is that a coincidence? It is separable. I can actually separate the equations here. What is that going to look like? Just go through the.
X times x equals v minus 4 over 1 minus v, all minus v.
Okay, can I do here?
Move the x to the right side and divide the entire thing by the right side that's currently there.
Sure, you can do that. Maybe simplify this first, or you combine these fractions.
The common denominator 1 minus v.
Right, you can do that. And so what this looks like is v minus 4 minus v plus v squared all over 1 minus v. So those v's would cancel. And basically we have dv dx times x equals v squared minus 4 over 1 minus v. How did you say we can continue?
Now we can move the dx over to the right side and then
Right.
move that whole
This entire thing can go under.
Yeah.
So if I divide by this entire fraction, it's the same as multiplying by the reciprocal. So this ends up being 1 minus v over v squared minus 4 dv. And this side becomes dx over x. Now everyone's separated. I can, at this point, integrate both sides. Now the right side is, of course, ln of x plus c. What is the left side?
do the quotient rule.
The quotient rule.
Would you do a trick sum?
V is
Quotient
equals
rule is a rule of differentiation.
V is equals secant, 2
Would you
secant.
do a trick sum?
Like a trig sum.
Unfortunately.
Jeez.
Yeah, it is.
Does anyone see it the other way?
Oh,
Because I'm not a fan.
Which we can't back
Do you guys remember trig sum? Do you guys even remember trig sum you're suggesting? You guys remember how to do trig sum? You guys remember what that entails?
Yeah.
Like if you do a trig sum when you don't have to, it's like twice the work. Is there another way?
It's the difference of difference of squares.
Okay, understand that.
Oh, so-
I don't know.
But he's just like, oh, I noticed this pattern. Like I'm eventually gonna end up with something that makes sense.
You multiply by
I have a
minus 1.
question. So like, let's say you test
Are we gonna have,
Wait,
you know, how we,
This,
we're gonna go on with like differential equations, right? We're gonna have something where we have to use trig sum?
well, can't you separate?
Potentially, yeah.
Well, can't
Like,
you
I'm
separate-
not gonna put it in.
Multiply by
Can't
minus
you
1.
separate them like 1 over v squared minus 4 minus?
Oh, yeah, he said difference of squares, I'm thinking he meant to think of it as that.
Yeah,
No,
I'm not good at talking today.
And then,
Separated into 2 integrands?
right, what is that called?
Oh,
You said-
partial fractions.
Partial fractions, who remembers partial fractions?
Okay.
You remember it? What is it, what are the pieces?
So the pieces would be, say when you find the zeros, the bottom part.
Uh-huh.
Oh,
and then
yeah.
you plug, and then
A over.
you plug it into the top. The bottom one works to find the variable like C1 divided by D minus 2.
Okay, like, what would it be here?
Oh, you don't.
Yeah, do it, like, yeah.
A over v minus 2 plus b over v minus plus 2 is equal
So
to,
v minus 2 is gonna be one of them, b plus 2 is gonna be the other one.
which is equal
Yeah.
to 1 minus
But how, what is the numerator?
1 minus
dv.
Huh?
Oh, wait, no.
A and B?
db.
A and B?
B plus 2?
a. You put a and b, which is equal to v 1 minus v.
Yeah, we have linear factors here, there's a shortcut. Remember what's the shortcut?
Like
I
a
don't know.
cover up?
Huh?
Was it a cover up method?
The cover-up thing, yeah, you remember what that is? How does that work? It's like the residue theorem, right? You had this out. Okay, so figure out what makes one factor in denominator. So this only works for linear factors. So if the power is a square, this does not work anymore. You kind of have to do the A, B, C thing and kind of do it the long way. There's another way, but it's kind of not worth the hassle. V equals 2 makes this 0. You cover that up and plug in V equals 2 in the result, right? If I plug in V equals 2, what do I get?
Negative 1.
Negative 1 in the top, what about the bottom? 4, so I get negative 1 over 4. That's the number here. V equals minus 2 makes this 0, cover that up, plug in minus 2. What happens now?
3 over.
You get 3 over negative 4, which is? Okay, so those are the pieces, right? This is partial fractions.
Will you do that again real quick? I've never seen that technique.
Yeah, I've never seen it either.
Yeah.
I don't know, I don't think that's the official name for it, but
I get it.
Technically, it's using the residue theorem on partial fractions. That's kind of the cover method. It works. Okay, so it's very important that you understand that this trick only works with linear factors. Like if there are squares here, it's not going to work. Okay, so figure out what makes this factor 0, the v minus 2, right? So we're focusing on the v minus 2. V equals 2 makes that 0. What you're going to do is you're going to cover that up, and you're going to plug in v equals 2 everywhere else.
Oh, is that it? That's all?
So if I plug in v equals 2, I get 1 minus 2, which is minus 1, 2 plus 2, which is 4, minus 1 over 4.
So that's quick math.
V equals minus 2 makes this 0, cover that up. Plug in minus 2 everywhere. If I plug in 1 minus a minus 2, that gives me positive 3. Plug in a minus in here, it gives me negative 4, so I get positive 0 and negative 4. That's the coefficient of that. Now that we have that, what's the integral of this?
Factor out negative 4 from.
Yes, what is the integral?
L of v minus 2.
Come again?
L of v minus 2.
Minus 1/4
Yeah.
ln of
Of v minus 2.
no,
Absolute.
Oh my goodness.
minus 3/4
L of the absolute value of v plus 2.
Plus C.
Plus C.
That's already in there.
Right, but well, see,
Yeah, I just have one question. I don't get, why would you write the plus on that side and not on that side?
It's like
it doesn't matter.
combining the constants.
I just move all the constants to one side.
Uh-huh, okay.
I'm used to writing plus C on the right side, that's why. Aesthetic reasons. There's no, there be no difference. Now, notice that there are no derivatives present in this equation. That's actually the solution. Now, of course, there's this variable v that's left over here, but we actually know what v is. I erased it. V just means y over x. So that is the implicit form of the solution. Notice that we haven't solved for the y's. Yes.
For this final answer, you don't have to put the coefficient as an exponent at the b minus 2? For the d there?
It depends on what your goals are. Like if you wanted to solve for the y, that's probably something you would do.
This
But
wouldn't,
especially since we have two different coefficients here, combining those are going to be annoying anyway.
this wouldn't be homogeneous, right? Because on the right side, there's no y over x. Would this be homogeneous?
Come again?
Would
Like
this-
the whole thing is called homogeneous first order. Like that's what this topic
On the
is
right
called.
side, it's not y over x, it's only x.
Yes.
So how would that be homogeneous? Because wouldn't the, every variable need to be y over x?
No. Homogeneous means the definition that I gave you before. For first order, that's what homogeneous means. It means that you can write as dy dx equals some function where you can think of it as y over x. That's what they call it. Now this here is the solution. It is implicit. I mean, you could simplify that a little bit, but probably not much more.
Does it have to be y over x, or is it just implying that it has to be some ratio of y over x? Like, can it be y squared over x?
No, it has to be y over x,
Okay.
or else this isn't going to work.
Okay.
Now, I wanted you to, and that's kind of that's going to be the answer. Like I could clean this up a little bit, but I'm not really interested. I'm not sufficiently motivated.
So this is just find an answer after this, right?
Yeah. And of course, given initial conditions, you'd have to find that plus c. But yeah. Now, let me tell you the general summary of how this thing works, as well as some remarks before moving on to a couple other problems. So, one thing to notice here is that we started out with y minus 4x over x minus y. And I want you to notice what happened when we multiplied by the 1 over x. 1 over x. Notice that what that actually did was it puts the y's, it divides all the terms by x's. Now, the x's, of course, became just 1, right? So they kind of canceled themselves out, right? So what I'm about to write down is going to make more sense because you're going to see what's going to happen. Notice that at the end of the day, after the substitution was made, of course, this is going to be its own thing, the dv, dx, x plus v. But on the other side, notice what happened. There's going to be a v in this position. There's going to be a 1 in this position. There's going to be a v in this position, right? That's what we ended up with. I want you to notice what happens. Notice that wherever the y's were, they're all replaced with v's, right? Wherever the x's were, they're all replaced with 1s. That's a pattern. So you're not going to have to go through the first couple steps that I made of doing this kind of thing and trying to figure it out. You kind of can notice what pattern, where it's going to go. So that being said, let's do some summary here. So you're going to, now it's going to make sense when I actually write it down. Homogeneous first order equations. So the form, and now remember what I mentioned like way in lecture 0 or lecture 1. Every time I teach a topic, there are two things you want to make sure at minimum you take away from the topic. What is the form of the equation I spoke about, and what is the strategy to solve it? So the form is dy dx equals f of xy, where? Now here's a quick way to know that this can happen even if you don't see it happening. It's going to be something that you're going to check for. constant times x times a constant times y is equal to the original function. Now, why does that make sure that this requirement is being fulfilled? Well, notice that if I replace x and y with a constant times x and a constant times y respectively, the constants will just cancel each other out. Nothing else is going to be affected, right? So it turns out that if this thing will work out, it means this is expressible as the form of a variable y over x, because it'll just revert back to its original function by doing this. So, for example, let me actually finish right now. So that's the form, and that's the check to know that you have the right form. So this one is a little bit more detailed. You write it in that form and make this check. Now, if the above holds, you're going to change the y prime to dv dx times x plus v, and you're going to change the f of xy to f of 1 comma v. Because as I explained, all the x's are going to be replaced with 1, all the y's are going to be replaced with v when we kind of do this manipulation. So this checks that I can actually write the function in this form, and once I do the substitution of v equals y over x, change this to that, this is a result of the substitution v equals y over x. All this is going to happen automatically, and it turns out that whenever this happens, this substitution will always make it separable. It will always be separable every single time. The new ODE will be separable. Solve it. Then replace your v's with y over x. That covers the first order homogeneous equation. Yes?
Can you, I'm not clear on what that check is.
I'm going to do more examples where I actually do the check, so you can actually see it in real time.
Okay.
Now, some remarks. Now, someone asked me earlier about some ugly integrations. It turns out that these guys often have ugly integrations. So if there's ever going to be a time where partial fractions is going to show up or a trig sum is going to show up, it's probably going to be on one of these problems. Right? It just turns out the integration just happens to be ugly a lot of the time. Maybe not ugly. No integration is ugly. You know. They're all beautiful. Everything. Okay. Right. So remarks. So I was kind of suggesting this to you since the first class, but now is the time to get your top 2 under control. It's not under control by the time you hit these problems, you are in trouble. Get your top 2 under control. So all those techniques, partial fractions, trig sum, integration by parts, you're definitely going to want to have like all of that down. Another thing that tends to be with these guys is it tends to be hard to find an explicit solution. So implicit solutions are often just accepted. It has to be like really easy for you to get to that y for you to solve for it. In most cases, I'd rather you just stop once you replace the v with the y over x.
You will stay
So it's kind of what I want to mention. Yes, I wrote some other notes here. But I kind of said them already. So, this works in general as long as the check holds. And when I'm referring to the check, I mean checking that f of a constant times x, constant times y equals f of x, y. Right, so there are no restrictions on the function x and y. It doesn't have to be linear, it doesn't have to have a special form. As long as this is true, this is going to work. So let's do another example. Now I'm also going to give you some tips on when this might work, although you'll notice one way to tell that it might be something that you want to check is if the power of each term is the same. Now by power I mean, if you look at all the variables in each term and you sum their powers, you should always get the same number. That's one way you can actually eyeball it to kind of see. Here in this term, the power of this term is a square because the variable is raised to a square. The power of this term is a square because the variable is raised to a square. The power of this term is a square because there's one power from here and one power from there. The sum of the powers is a square. But here's what I want to do. So one thing I could check is that this isn't linear, and is it separable? I'm going to look at this as a homogeneous. So here's what the check actually means. So this guy is my f of x, y over here. So what I'm going to do is I'm going to find what is f of lambda x. Sometimes it's hard to write like kx, ky. I used to do that, but the kids used to giggle at ky. So look at that, right? What's going to happen is I'm going to plug in 3ky squared minus kx squared over 2kx ky. What you're going to notice now is that in the top, k squared is common. I'd be able to factor it out. Equal to, well, this would be k squared times, well, 3y squared minus x squared. In the denominator, again, I have two k's multiplying, so that's a k squared, I can factor out. I'd be left over 2xy. Notice that the k squareds would cancel in this case, and what are we left with? Well, that was the original function. So that check means homogeneous. That guarantees you'd be able to express this function as a function of y over x. Now you don't have to actually go through the algebra to get this done. Once you notice that this is going to work, you're going to go back to the original, you're going to replace all x's with 1, you're going to replace all y's with v, you're going to replace your dy dx with dv over dx times x plus v. So this immediately implies that dv dx times x plus v is going to be equal to, I'm going to go there, everywhere I see a y, I'm going to put a v, everywhere I see an x, I'm going to put a 1. After the substitution, that's what it's going to look like. I can just jump to this step. Now, as I mentioned, this will always be separable. And so this is
You just use the coefficient that was attached to the x squared for the 1, right?
Come again?
You just use the coefficient that was attached to the x squared for the 1, and the previous squared minus 1. did we get the 1 for when we replaced the x?
Because if I replace x with 1, I get 1 squared, which is 1. What do we do?
What?
Oh, okay, we're actually, I get it now.
I mean, literally replace the x with 1.
Yeah, for some reason I
Literally
thought we
take x out and put 1 in it.
were, I thought we were dividing by 1 over x or something.
Technically, to get this one into the right form, you divide by 1 over x squared in the top and the bottom.
Oh,
But
okay.
I don't want you to have to figure that out. So I'm saying, whatever algebra you do to get it to fit, it will always be equivalent to replacing the x with 1 and the y with v. It's always going to work out that way.
Okay,
So multiplying top and bottom by 1 over x here is not actually going to do it.
you gotta do 1 over x.
You'd have to do 1 over x squared. So here you get y squared over x squared, which is like y over x all squared. You get 1 here. Here, if you divide xy by 1 over x squared, the x's would cancel. You'd have an x left over in the bottom, and you'd have the y over x that way.
Okay.
And equivalently, what's going to happen is all the y's are going to turn to v's, all the x's are going to turn to 1's.
How'd you get the left side? That's always true for all homogeneous equations?
Thank you.
Yes, this was in the summary.
Oh.
Right? Once you set v equals y over x, it automatically means that y is equal to v times x. So if you find y prime, product rule, it'll always give that. So I'm giving you guys the shortcuts here, the little tidbits, like I'm trying to make your life easy. I'm just telling you, what's going to happen is, all y is going to change to v, all x is going to change to 1, and your dy dx will always change to that every single time. That's the pattern. Once this works out, that follows automatically.
So we're better off just doing this check, basically, whenever we want to know if it's going to work or not, right? Not actually going through all the algebra and seeing, this is quicker, right?
Basically, you always check separable, then linear, and if those two don't work out, this is something you would look for.
Okay.
And then you would do this check. Now, assuming you do this check and this works out, this is automatic. Y prime gets replaced by this all the time. All your y's get replaced by v, all your x's get replaced by 1.
So it wouldn't be a bad first choice if you've already taken one of the other choices and said that it's not possible for another choice?
For what other choice?
So like if I went in and just did this immediately, so I felt like it was the right thing,
Oh, yeah.
I could just get it on
If
the
it's
first try,
homogeneous, it's always
rather than
fine.
having to go through the other stuff.
to y, x to y.
If the other stuff would have worked,
Huh?
it would be easier to apply.
Okay.
So if you're going to solve it this way, like I said, the integrals are going to tend to be harder.
Okay.
And it's going to tend to be harder to solve for the y at the end of the day.
So you could be in a situation where you can solve it this way.
You could be in a situation where you can solve it this way and at the same time it's linear and at the same time it's separable.
Oh, okay.
But you choosing this, you're just giving yourself more work. You should look for the other two first.
About this shortcut, if you keep using it, do you lose anything, like you miss the ability to identify patterns, and when you come across like a different ODE, you won't have the pattern recognition skills? Would that ever like
No, if you do this, it's separable, and there is no pattern. Separable just means integrate both sides.
I mean,
There's going
you
to be
keep
no
a
other
shortcut,
pattern
like,
to-
you know,
There's going to be no other pattern to recognize. Separable is already a pattern. Separable just means separate the variables, integrate both sides. That's what separable means. Once you know something is separable, you don't have to look for anything else. It's Calc 2 at that point. Okay, so we end up here, and we're going to do the same thing. Move the v to that side. And more space here. We're going to have dv dx times x equals, now this we're going to multiply by 2v over 2v to create the common denominator. So 2v is going to be on the bottom, on the top is going to be 3v squared minus 1 minus 2v squared. This is going to look like, well, v squared minus 1 over 2v.
Do you have to square the 2 into v squared or no?
Coming in. I'm coming combining the fractions. So now it's separable, move this over there. That's going to look like 2v over v squared minus 1 dv equals dx over x. How do you integrate this?
Fractions and the cover of them.
No.
Oh yeah, use
Come on, you can't use it on that?
You could use u sub. V squared.
Substitution. Why would you do partial fraction?
I just learned how to do
U equals v squared minus 1. The du would be 2v. Regular substitution would be the choice here. Now you're going to replace this with y over x. This one happens to not be a messy integral. I said they tend to be a messy integral. This just happens to be a nice example. Don't just think it should be complicated, so no, just take the integral as it comes. If you were faced with this, substitution would be how you do it. Yeah. I mean, we could simplify that a little bit, but I think we would be fine on that thing.
How would you find this more explicitly? Like, what steps would you take?
Combine the fractions here, split the logs, bring all the log x's to one side, e both sides. Because you have log of a divided by b is log a minus log b. Do all the logs. Yeah. Try these. So try this one. We'll finish it on Wednesday. We'll finish these two on Wednesday. Come in. On Wednesday. I mean, there's a slightly nicer way to write this, but I won't mention it. It'll still be in implicit form, but without the logarithms. Anyway, so try that one as well as just, I want you to know, homogeneous first order is one example of a larger system of strategies. I don't know what I want to call it. Which is called substitution, it turns out. So this is substitution for differential equations. And it just so turns out that when this particular pattern presents itself, the substitution of v equals y over x is going to be the way to go. However, there are possibly others. So here's an example.
What's the NB stand for?
Note.
What does B stand for?
It's an abbreviation of the French phrase for know well. Nota bene. Or is it a Latin phrase?
I think it's Latin.
It's Latin, yes. It's always Latin. Math is such pretentious. Call us lambda. Let's use the Latin phrase for this. Okay. Here's an example. dy dx equals 4x minus y plus 1 all squared. This is not homogeneous, but it is something that a substitution can work. Here's what I want you to try. Solve using this substitution. Use v equals 4x minus y. As a substitution, kind of go through the same kind of steps that I did for these, but the same pattern is not necessarily going to present itself. But you can actually solve something like this using substitution. Notice that it is also not linear or separable. And it's not homogeneous. This is not anything like we've seen before. But this substitution can actually conquer that.
If we added +1 to that, it wouldn't work.
try it. I mean, that one works. Try the plus one. We'll solve it for now. We'll get rid of these two and we'll talk about some new stuff. And we'll finally get out of 2.2 next time. 2.3. I think we'll spend the entire class on 2.3.
Do we have to do 2.2 homework?
I believe so.
Yeah, so.
Oh, that's something I should mention. Now, some of you got away. In some sense, it's good for you. In some sense, it's bad for you. But believe it or not, web work has no homogeneous first order problems.
What?
Like the entire web work system, I've searched the entire system, there's no problem where that uses this. There are other substitutions, but there's not this particular substitution.
What are you saying?
What I'm saying is, if you want extra practice, use the text problem for extra practice. Which I listed in the syllabus in the section 2.2, I listed a bunch of practice problems. These test problems for practice.
Should we be okay with the 2.2 homework now?
Yep.
This is 2.2 today, right?
Yeah, this is the last thing in 2.2. So on Wednesday we'll do 2.3.